Okay, so this lesson is going to focus on using the dot product to determine something we call a scalar and a vector projection of one vector onto another. Okay, so scalar projections is essentially how much one vector shadows another. Or another way to think of it, how much of one component do they have in common? The order is important, once again, A onto B. So if you're projecting an image, you're taking it from one area and putting it onto another. So if I have vectors A and B, so I'm just going to draw a representative vector. So I'm going to say that this here is vector A, and this here is vector B. Okay, so that's any two vectors that we're going to talk about. Now, right now, if I were talking about the projection that's happening, you're going to take A onto B, you start at the tip of vector A, and you drop a perpendicular down to the vector you're going to hit. So this is the perpendicular line. So this right here, that represents the projection. So vector A is projecting, or has this much of vector A that overlaps with B. So that's the easiest way to think of it. It's a shadow. How much does A shadow onto B? Now, if the angle between them is less than 90, the projection is positive. So you can take this diagram, you can see it's positive. It's going along vector B. But if we have an angle that is more than 90 degrees and less than 180, so if I have vector A here and then vector B this way, so if I'm saying that this is A and this is B, I have an obtuse angle in between them. If I go to draw a perpendicular line from the tip of A, so let's pretend that's straight, it doesn't actually hit B. In order to hit B, I need to extend it. So that's this yellow line. So this part right here, that represents the scalar projection of A onto vector B. And it would have a negative value because it's an extension of B in the opposite direction. Now, let's go and look at this little diagram right here to talk about what would happen if we were to do the projection of B on A. So I'm going to redraw that little picture. So I have B, I have A. Okay. So this time I go to the tip of vector B and I draw a perpendicular. So the projection becomes this yellow section. So you don't always have to have the vector being flat that's being projected onto. It just really depends on how you draw the diagram. Once again, this would be positive because it's along the direction of the vector. You'll notice I didn't put arrowheads on any of these yellow lines because scalar projection is a scalar quantity. It's a number. The notation for this here looks like this. So projection, so a magnitude bar projection. So for this one right here, it would be B down below and then A right here. And the reason why, you can think of it, it is A onto B. And actually I just realized that this is not this one right here. That would be the notation because it's A onto B. The B is down below. Now how do we actually figure out this numerical value? Of course we have a formula. So we have the scalar projection of A onto B is the dot product divided by the magnitude of B. Now if I were to simplify that a little bit again, and we talked about the projection is the shadow on top, if I simplify this, A dot B can be written as the magnitude of A times the magnitude of B cosine of theta all over the magnitude of B. Mathematically, the B's cancel out, and you're left with the magnitude of A cos theta. So if you think about what we've learned, this is simply the component of the vector that you're being projected onto. Same thing down here. You'll notice A onto B, the B is on the denominator. b onto a, the a is in the denominator. In general, these two numbers are not equal to each other. However, they will be equal to each other given one specific angle. Or, well, actually, it would be two angles where they would end up being equal to each other. Okay. Now, here's an example. So given the vectors below, calculate each scalar projection. So projection of A onto B. So I'm going to put B down here, and I have A. And because it's scalar, I need my magnitude bars. It's A dot B, and because I'm projecting onto B, it's the magnitude of B in the denominator. So when I do A dot B, I'll have -2 multiplied by 1, because remember cross product, we multiply the x components, and then I'm going to add the y components after they're multiplied, and then the magnitude of B will be 1 squared plus -2 squared. And again, we're expecting to get a number. So this here will be -12 over root 5. Now let's do the same thing, but for B onto A. So I have the projection. A will be down below. I have B. So I have A dot B over A. So that -12 is still the same, but now the magnitude of A is going to be the root of 29. And I got that by squaring the x and the y components, doing the Pythagorean theorem. Okay, so again, number is the result. Vector projection, very, very similar. So if I have vector A onto B, I'm going to draw it the same way. I'm going to draw a perpendicular once again. This here is going to be the vector projection, but now all of a sudden I have an arrowhead because the result has to be a vector. So you'll see this here is the scalar, and this here is the unit vector. So by multiplying by the unit vector, you're maintaining the direction of the vector to turn it into a vector projection. If you multiply the magnitude of B, you end up with the magnitude of B squared. So this is the best formula to use for vector projection. So again, so projection A onto B. So the B will be in the denominator, the A up top. You'll notice this time I don't have any magnitude bars, okay, because it's an actual vector that we're going to end up with this time. So let's do an example. So I have vector A is 5, B is 1, and the angle in between them is 50. And it's asking me to find the projection of A onto B. So I have projection, B is the subscript, then I have A equals 5 multiplied by 1 times the cosine of 50, since that's the dot product, all over the magnitude of B squared. So that's 1 squared times vector B. So when we work this out, we're going to get 3.21 B. I know the answer looks funny, but the B means that it's 3.21 units times however long vector B was. What if it's in algebraic vector? So start off the same way. So projection of A onto B. So again, I'm going to do that dot product. So I'll actually write out the formula again since I didn't write it over there. So A dot B over the magnitude of B squared multiplied by B. And I know that it's a denominator of B and a B right here because I'm projecting onto B. So A is going to give me 2 minus 12 over the magnitude of B is 1 plus 16 all squared, and vector B is 1 and 4. So this becomes -10 over 17 times 1, 4. So that becomes -10 over 17, -40 over 17. So the result is a vector that is a multiple of vector b. And that's always going to happen with the projections. Whatever vector you're projecting on, that is the vector that you're going to be determining the multiple of. Okay, the third thing that we want to talk about here is something called direction cosines. So we're not going to go into a lot of the theory here in terms of where this math is coming from. However, they are useful for figuring out specific angles with the specific axes. So there's three different axes we're working with, x, y, and z. In order to find the angle that vector A, or any vector, is going to make with the x-axis, you'll notice that we have the x component on top over the magnitude of the angle, and then of course you'll have to bring the cos to the other side and do the inverse. If you're finding the y-axis angle that it's making, so that would be this, this angle right here, so this beta value, if you were to calculate this value right here, it will be the y component. So this is like the x component. This is the y component. This, and the magnitude isn't going to change because the magnitude of vector A is not going to change. And then finally the third one, vector C, or not vector C, component C. So that's the gamma symbol that they have up here. So that's the angle that this vector is making with the z-axis. Now, this vector right here would have the coordinate based on the picture that we have here, A, B, and C. So that's where those letters are coming from. Okay, so I'm actually going to make this look more like a Z and less like a symbol. So this here would be Z. So this is just another way that you can sort of see that this vector right here, if you were to turn it into 2D, that is the angle it makes with the x-axis. The angle with the y and with the z. Depends on how you can visualize it. All right, so that concludes the lesson on vector projection and direction cosine. So hopefully it makes sense. The big thing is recognizing that a projection is a shadow. One of them, the scalar, just gives you a numerical value. It gives you the x component that is being overlapped. And then the vector projection, it's the component that's being overlapped, but the vector notation is maintained.